with that, Leo's going to tell us about frustrated quantum magnets and Majorana edge modes and so on. Let's welcome him. I guess you all know him. He's at UC Santa Barbara and KIT. Let's welcome him.
Okay, thanks, Una. Yeah, so the plan, such as it is, maybe it'll evolve, but I'd like to talk about quantum spin liquids. I'm going to start with kind of a broad introduction, and then I want to turn to talk about ultimately talk about some recent experiments which stimulated us to think, come back and think about thermal Hall effect. We found some things I thought were kind of interesting. So the plan will be basically start with a general introduction. So how's this working? Is this all right? Quantum spin liquids. And then I'll talk about Kitaev's non-abelian spin liquid. Thermal Hall effect. And alpha routine trichloride. And maybe it doesn't sound like there's any relation, but there will be phonons in the last part, so to speak. Make some connection to 60-year-old physics. So for the first part, there are lots of actually great references, but I'll just advertise. We wrote a review article a couple of years ago in ROPP, which is pretty long and covers gives us kind of a longish review to that subject. But I'm not going to assume that you know much about it.
What is ROPP?
Reports on Progress of Physics. Correct? I think Nandini's an editor. Okay. Quantum spin liquids are kind of an old idea. They have a long history. I'm not good at history. Never was, even back in high school. But the idea was originally envisioned by Anderson, somewhat inspired from ideas of Linus Pauling, coming from thinking about the chemical nature of the electronic state of benzene. We tend to think of quantum spin liquids, they had their origin in thinking about physics of small spin Heisenberg models. So maybe we want to start there. Think. Have a Hamiltonian, think about an antiferromagnet. Ferromagnets are a little too simple. Just something like this, spins interacting between nearest neighbors, where the spins are taken to be in their smallest spin representation, s equals a half. You all learn in class that for quantum spins, there's a classical ground state that you might guess, which is no longer an eigenstate of this Hamiltonian. If I think of classical spins, there are many lattices on which this Hamiltonian is what would be considered frustrated. Nice example would be Kagame lattice. For some reason, people put the accent here, which is kind of bizarre to me since it's a Japanese word. I don't know. They put a French accent on it. But we consider something spin Hamiltonian frustrated. Most of them are really. If it's not possible to separately minimize each term in this sum. Okay? So each term in the sum just wants the two spins classically to be antiparallel, but of course you can't make all three spins on a triangle antiparallel. Even so, the model of course has a classical ground state. If we wanted to put classical spins on it, they would do something like this. The best you can do is make all three spins on a triangle add to 0. Okay. But there are many ways to do this. I have a lot of freedom in how I put these remaining spins. I can even rotate them out of the plane. There are many, many degenerate classical configurations. So there was an idea long ago that because there were so many different classical configurations that would be classical ground states of this, once you incorporate quantum fluctuations, the system could sort of develop a superposition of all these different states, which might have a lower energy than any classical state. Veit Elser here was one of the people who worked and proposed these things early on. Kind of extreme limit of a non-classical state would be one which, unlike this sort of classical configuration, maybe I should associate a state with it. We can imagine a classical state. This is something where I take a product over every site, and on each site, bless you, I just take a local eigenstate of spin polarized along the axis, let's say half axis of the classical spin configuration. I just take a product state like this. And that's the kind of zeroth order classical approximation to a quantum state. But it's not even an eigenstate of that Hamiltonian, but maybe it's a reasonable approximation. Let's see, there's another one back here. Or this is already it. Oh, this is it, great. Okay. It's interesting to compare with the very quantum state. If I just have two spins, then the ground state of this is just a total spin 0 state. So I can write this as j over 2 s1 plus s2 quantity squared minus a constant, which is j over 2 s1 squared plus s2 squared. Okay, and for spin 1/2, the square of each one of these is 3/4, so this is minus 3/4 j. You know from the rules of angular momentum that this total angular momentum of the two spin 1/2 could be either 0 or 1, so the ground state of this is just choosing this total quantum number to be 0. So that's a spin singlet state. The ground state for these two spins is just 1 over square root of 2 up, down, minus down, up, which is some unitary rotation of the EPR pair state. And so this has an energy which is minus 3/4 j. It's kind of surprisingly largely negative. If you think about classical spins, classical spin 1/2, it basically has length 1/2. If we took our classical state, which is just best classical state would just be a product state like this, one spin up, one spin down, and take the expectation it's not an eigenstate. You can write this S1.S2 out in terms of, bless you, X components, Y components, and Z components. The X and Y component will flip one of the spins, and it will be orthogonal to the other state. So the only contribution will be the ZZ component, and this will be just J times SZ in this state times SZ in this state, which is negative, which is good, minus J over 4. So this, for two spins, this obviously is way better. Now, suppose we want to build this kind of very quantum state, and you can think about this as kind of quantum fluctuating between the two Néel states on two sites. Suppose we want to do this on some lattice like the Cagney lattice. I'll try and repeat this, well, we can choose to pair two spins into a singlet. So that means that my wave function has to be a wave function of all the spins, but I can take these two spins and put them into a singlet and take a product of that wave function with another two spins being a singlet, maybe like this, like this, like this, like this. Again, I have to use up all the spins. So this is and these go off somewhere. Oops. Crap. All right. Oh, we lost that one. That's interesting. There's also an eraser there. Several erasers. There's a lot of stuff there.
I dropped one of those erasers.
You did that? Well done. There won't be any more colored drawings for the rest of the school, unfortunately. Very good. Okay, so we can take this this is sometimes called a valence bond state. Psi valence bond is something like a product over these pairs of sites. And then for each pair of sites, I take a singlet. So this is not an eigenstate either, but we can use this as a variational state and compare it to this variational state. This gives us some idea of how this kind of more quantum ground state might compare to this very classical ground state. Okay. So let's do this for the example of this Calumet. So let's look at the classical one. We'd like to evaluate this. Okay. So the best thing I can do classically, as I said, is to make all three spins on every triangle add to 0. So we can bring this out by writing rewriting. So H is just this nearest neighbor exchange Hamiltonian. I can write it as a sum over triangles. And on every triangle, I add SI and square that. If you think about multiplying out this square, it's going to have S1 squared plus S2 squared plus S3 squared minus some products. Yeah, question?
So what about singlet pairs beyond nearest neighbors?
Oh, that's fine. There's no obvious reason to do it if I want to minimize the energy of this Hamiltonian. Okay. So far I just started about 2 spins. Here there's no obvious reason to do it because I'm trying to actually write a wave function that minimizes this. So I'm trying to build in correlations between nearest neighbor pairs. No obvious reason why I should build in any correlations between further neighbor pairs. They're certainly fine. They're allowed. I'll come back to the question about what do these wave functions mean? What does it mean to be writing down approximate wave functions?
I mean, will they have specific weight to the actual ground state of the problem?
Sure. Absolutely no problem with that. Okay. More general wave function would have it, but I won't be able to make a simple estimate on the blackboard. So I want to do that. Okay. So if you multiply this thing out, there'll be some constants. That'll be 3 times 3/4, remember, from the S squared here. Okay. I want to multiply this by J over 2, because each one of the bonds came in with a factor of 2 when I multiply out the square. Okay. So I can, and you notice that on this Calumet lattice, every bond appears in one and only one triangle. Okay. So that's an expression for the Hamiltonian. If I take the, so this tells you that classically, clearly we want to have I a member of delta of SI equal to 0. That's how you can see that this is the ground state of it. I guess there are various ways to actually evaluate the energy. Let me do it slightly differently, actually. Let me just continue and go back to writing it like this. Sorry, I was trying to be too clever. So this is the same as this. Let's see, I need more space. Let's bring this guy up. I guess I have to erase this. I want to keep that formula. There's no good way to use the third board, huh? Yeah, all right.
You can use the mobile board.
No. I'm not that desperate. So we're supposed to erase the classical ground state, but remember the classical ground state is just a product over sites, SI.n hat equals a hat. So to minimize that classical energy, we have to find some configuration where these spins add to 0 on a triangle. That condition for 3, basically this comes down to n1 plus n2 plus n3 equal to 0 on every triangle. That condition requires that they're at those 3 vectors are at 120 degrees from one another. Just geometrically about that condition. Okay. That in particular means that for any 2 neighbors, their relative orientation is minus a half. It's like a cosine of 120 degrees. So if we take the expectation in this classical state of H Kagame, it's going to be J times the sum over every bond. Since it's a product state, this is an expectation value of SI dotted into expectation of Sj. There's no correlations between the sites, and each one of these is just J is a half. It's a magnitude times this dot product, so times minus a half times the sum over every pair of nearest neighbor bonds. Okay. So the classical energy is minus J over 8 times the number of bonds. Who knows if I actually did it right? Should be nice. Possible, huh? I think it's right. Okay. Now let's compare to the energy of this valence bond state. Okay. So there's this valence bond state. We want to find this is the expectation of psi valence bond. H Kagame psi valence bond. So again, this is just J times the sum over nearest neighbors, psi valence bond, SI dot Sj, psi valence bond. Okay. Now this expectation value depends on which I and J we take. Okay. If I and J are not in the same valence bond, those 2 spins are completely uncorrelated. And so for those, that's expectation value factors. Becomes just expectation of SI dot expectation of Sj. But in these states, this is a total spin 0 state, so each of these expectation values is 0. So we only get a contribution when I and J are in the valence bond, in which case this is actually the quantity we just worked out. This is minus 3/4. So this energy is minus 3/4 J times not the total number of bonds, but the number of valence bonds. Okay. And if you look at the picture, you can see we can't cover all the bonds. Some fraction of bonds are covered. Okay. Let's see if I can work out what that fraction is. So here's a simple argument. I think it gives the correct answer. You can try to convince yourself whether it's right. Let me look around any given site in the lattice. If I look at any given site I, that has to be involved in some valence bond. So the fraction of valence bonds around any given site that are covered by a valence bond is just 1 divided by the number of nearest neighbors. In this case, it's 1/4. Now, the total number of valence bonds, the total number of bonds is just the sum over the number of bonds coming out of every site divided by some factor. Okay, basically divided by 2 because every bond is shared by 2 sites. But the fraction doesn't change if I do that. The fraction number of valence bonds that are a fraction of that is the same. So the total fraction is 1/4. A little surprising when you look at the picture. You might think, well, okay, every triangle's got 1 valence bond on it, and so 1 out of 3 is covered, so the fraction is 1/3. I leave it to you a conundrum why it's not true. Okay. Notice that this is smaller. Okay. This is the correct answer.
Yeah, yeah, it doesn't have any.
All right. So this is -3/4 j times 1/4 times the number of bonds. Yeah. Okay. So this is -3/16 j times the number of bonds. Okay. And it's kind of nice to leave this 1/z in here. If you just compare it. So this is actually quite general expression, right? And this is true for Kagame. So if you just compare this, 3/16 is bigger than 1/8, that's 2/16. So this is more negative actually for Kagame. This naive estimate would say this is better. Okay. But clearly this starts doing worse the larger the number of neighbors you have. Okay. So low dimension is kind of good. Now we haven't done as best as we could. This is this kind of state, what I call the valence bond state. It's still a pretty simple state. This is what people usually call now a valence bond solid. That's not what we would call a quantum spin liquid state. Okay. It's a non-magnetic state. In terms of symmetry, it doesn't break the spin rotational symmetry of the Hamiltonian. More fundamentally, it doesn't break time reversal symmetry. But it's still basically a product state. We wrote it. It was a product over some pairs of sites of singlets. So that wave function has absolutely no correlation between spins that are far away. In a more modern language, we say that this is a completely unentangled state. There's no entanglement at long distances. So I like to say this is kind of product-like. This one actually is a product. Well, that's interesting. So Anderson's idea was that you could improve on this wave function, which is not satisfactory in some ways. I got rid of the picture, but now we don't have the orange anymore. So maybe the red will still be visible. Okay. To draw this wave function, I had to pick a set of valence bonds. So this is actually breaking lots of symmetries. It's not breaking spin rotational symmetry or time reversal symmetry, but it's breaking lots of lattice symmetries. So what Anderson thought to do is, well, let me make a more interesting state, maybe a better variational state, by moving these guys around. Some other ones, I didn't do that. So a state like this, there are lots of ways I could do this, but if I think about superimposing a huge number, I try to superimpose basically every possible valence bond covering like this. This is what would be called a RVB, which stands for resonating valence bond. So, clearly if I allow myself to write states like this and I put different coefficients in front of them, quantum mechanics allows me to superimpose these with whatever coefficients I want, I've introduced a lot of more variational parameters, I can lower the energy. So it's not implausible that a wave function like this, which is already better than a classical state when I start just with a product state, could be made very, very good. And after decades of thinking about these things, work of many, many people, including Steve in a former life and other people, we now understand that this RVB state is kind of an example of a class of, a very broad class of highly entangled quantum states, things that we call quantum spin liquids. This is certainly very hand-waving, and it's quite hard to work with these things. It's very hard to work with the original Heisenberg Hamiltonian I wrote down. It has, really no small parameters at all. It has no dimensionless parameters other than maybe one. And so, really answering the question of whether an RVB or quantum spin liquid state is the ground state of this Kagame Hamiltonian has vexed people for decades. It's really a matter of doing a really good computational study. Okay? And it's proven to be extremely difficult even by this. However, the states themselves are very interesting, and we've, I think, as a community, been able to convince ourselves that at least in model Hamiltonian, states like this do exist. I'll give you some examples of that. And we understand much better kind of how to think about these states and their properties. What I'm not going to do is ever try to talk about whether or not any given quantum spin liquid state is a ground state of any given kind of realistic model. I'm certainly not going to talk about numerical studies of them. But I want to talk a bit more about these wave functions, how you can think about them, and how they lead to some physical picture. Before I kind of move on to these questions that eventually lead us to thermal conductivity. If you're faced with a wave function like this, you ask, how could I even really write down this full wave function in some form? Okay, that's already very hard. There's a huge number of possible coverings like this. I have to find some way as a theorist to index them and figure out how to write what these coefficients are as a function of which covering they are. Even when I draw the picture, actually the picture is not unambiguous because there's a sign in the definition of the singlet wave function. And having just drawn the picture, I would need to define the relative sign between these two configurations, for example. So there's really a lot of ambiguity. Okay. People have figured out various ways to work with these. The one I want to talk about, though, which turns out to be quite practically useful, and leads to a little bit of intuition anyway, is wave functions based on Gutzwiller projection. So this technique is sometimes called Parton technique. And now I'm drawing on the one that doesn't move, of course. Let's see, let's go back to here. So it's kind of amusing. You might amuse yourself by trying to estimate how many parameters you would need to describe that wave function if I had, say, 300 spins. So the rough idea, maybe one way to think about these part-time wave functions is we know we're trying to write down a very highly entangled state, something that's nothing like a product state. So we want to kind of start with some prescription that allows us to write down states like that, which are very, very entangled from the outset, and then build spin wave functions from them. And luckily, we do know how to write one set of wave functions that are very highly entangled in real space, which is by working in momentum space. Okay? Just a momentum eigenstate is something that's very distributed in real space. We want to take particles and put a lot of them in momentum eigenstates. That's a way to build real space wave functions. A way to do it is to so we can always represent spins using what are called Apergosa fermions. Okay, so these C's are spin 1/2 operators. Alpha is up and down. C's, S's live on some sites like this. Okay. And C's are just canonical complex fermions. If we impose this constraint, so these alphas and betas are summed, that is, we put one fermion on every given site, and one fermion has to have either spin up or spin down, so that we've effectively built a spin 1/2 on every site. Okay. You can think about these as the underlying electrons in a spin 1/2 system. Okay. What we can do is try and form some kind of plane wave states. Take some state like this, CK alpha, which is sum over sites, like k dot Ri, Ci alpha, so i's are sites of the lattice. Maybe I should normalize it by 1 over square root of the volume, something like this. That defines some plane wave basis. And then I just can form some state by taking a product over some k's of ck up dagger, maybe ck down dagger on the empty state. I don't have to take spin up or spin down eigenstates. I can take other spin eigenstates. I start acting with a bunch of fermion operators like that. You can imagine, for example, I fill a Fermi C. This is momentum space. That gives me a certain wave function. This is, in general, this will not have a single occupancy on every site. I can arrange by just choosing the number of momentum to be the number of sites in the system that I have the right number of fermions, but then to get a spin wave function, I have to act on it with some projection operator, called the Gutzwiller projector, to get a spin wave function. But this is kind of the Gutzwiller projector is kind of a machine. This projector is just a product over sites that should remove any doubly occupied sites. Something like this. So as long as I put in a number of particles that are equal to the number of sites on the lattice, and then then either I get various components in this wave function if I were to write it out in real space. Real space, this is a mess. It's a sum over all different kind of fermion occupations. If I'll find some components where every site has one particle on it. Those are good. Other components, if they'll have some sites that have no particles and some with 2. The total number is conserved. Those will get eliminated by this. I might do something which doesn't conserve the number of particles, and then I have to be even a little more careful. I should project out the empty sites as well. Good. Now, I actually have a ton of freedom here. A state like this, I'm just filling some kind of free electron states. I could even make it more abstract. I'm just going to take a product over some states n. I call them, I don't know what we call them, psi n dagger on the vacuum, where these psi n are eigenstates, some unitary rotation of the original single particle on-site states. And I can still carry out this procedure. Right. So which state should I choose? Well, the natural thing, I'm looking for a ground state. I should choose these states to be the ground state of some fermion Hamiltonian. So this is kind of a nice procedure. We choose psi to be the ground state of some free fermion Hamiltonian. So the only real restriction here is that this Hamiltonian should be quadratic, so we can solve it. And maybe we want to impose some symmetries on it. That's actually a little bit of a subtle thing, what symmetries we should impose. So what kind of quadratic fermion Hamiltonians do we know? Well, we know a lot of them. Okay. We could take a Hamiltonian of a metal. Means our Hamiltonian might be something like, this is not the real Hamiltonian, let me call it, I don't know, H mean field. Okay. Something like sum over I and j, T, Ci dagger, Cj. And we put some chemical potential so we can control the number of particles in it. We can choose the ground state of that. We could choose it to be something like, could be a semiconductor. Could be something similar to this. Let me write it more general, some Tij, Ci dagger, Cj, and maybe some, for example, we could put a potential so that we raise the potential on one side and lower it on another. That's a nice, easy way to open up the semiconducting gap. We could choose something fancier. We could choose a semi-metal. Something like graphene, or some fermions with pi flux. We can fit that into this form. Okay. So that instead of having a Fermi surface, we have some Dirac cones. And we can make a superconductor. Superconductor is also quadratic. We can have our Hamiltonian as not only some hopping, but also some pairing. These are all legitimate choices. As long as we choose them to be translationally invariant, then we can at least solve these mean field Hamiltonians by going to K-space, and we expect them to have kind of isotropic densities. We could get even fancier if we want, make charge density waves, such things. Now, for each of these states, these give us a variety of these kind of, we call them mean field or fermion wave functions. And they lead us to some spin wave function by Gutzwiller projection. So you can kind of see from this we could write down a huge variety of different highly entangled wave functions that are all kind of candidate wave functions for quantum spin liquids. So what do we really know about these things? So, yeah, lots of questions. Sorry, I should have turned around more. Go ahead.
So we started with the condition of the that the Ci dagger Ci alpha sum over alpha is 1.
Right.
How the projection operator is keeping that condition to be true? Because we are
Okay.
having a chemical potential here in some of the.
Yeah, in some of the cases I need to do a little more than this. I should, in general, want to write this as just a projection operator onto the states where Ni is equal to 1. I can write this in various ways. If the total number is conserved, all these cases except for the superconductor, the ground state of all these number conserving Hamiltonians will have a definite number of particles, and I can choose it to have the number equal to the number of sites. And in that case, the number of doubly occupied sites is exactly equal to the number of empty sites. So it's sufficient to project out doubly occupied sites. However, if I take a wave function like this one, and that's not sufficient actually, I need to take a more general projector like this, which just projects out both empty and doubly occupied sites. Does that answer your question?
Yes.
Yeah. Okay.
Yeah, is the high entanglement coming from the fact that it's a fermionic determinant that you're constructing, or is it coming from the projection?
No, I mean the original state is typically more highly entangled than the projected one, actually. Okay. Yeah, that's the purpose. Okay. Yeah, so these have varying degrees of entanglement. I'm not really going to worry about that here. That's not. It's very difficult. Ultimately, what my goal here is to get towards telling you about some quantities that could actually be measured, would be actually signatures of quantum spin liquid states. And entanglement, unfortunately, doesn't seem to be one of them, except in a simulation. Okay. So let me just tell you what we believe. This is like a confession of religion or something. Okay. We believe that for each one of these kind of free electron states on projection, we get a wave function which is kind of characteristic of an actual spin liquid phase of matter. And so I'll write down this correspondence. Okay. Actually, the simplest example turns out to be the superconductor. Imagine it's an S-wave superconductor. Let me write SC. Okay, so we expect that our mean field Hamiltonian for an S-wave superconductor would have a full gap. And if the Gutzwiller projection is somehow not too drastic a thing, we might expect that the corresponding quantum phase would also have a full gap. This is a very crude argument, but it's substantiated by quite a large number of calculations. We believe this actually corresponds to indeed a gapped topological quantum spin liquid state. And I'll explain what this means. This is usually what's called a Z2 quantum spin liquid. Probably the next degree of complexity would be a semiconductor. That's also gapped. There's a difference, though. The semiconductor conserves a number of particles, whereas the BCS superconductor doesn't. So this Hamiltonian and the one for the semiconductor, they both possess the property of having a gap, but they differ in their symmetries. And so this one, the superconductor has very little symmetry. The only thing it really conserves, apart from spatial symmetries, which I'm not going to worry about, is the parity of the number of electrons. This is kind of the number of fermions. This is kind of a fundamental property of fermion Hamiltonian, since the Hamiltonian should be a number, should be a boson. So mathematically, this Hamiltonian has some Z2 symmetry under changing the sign of these fermion operators. That symmetry has no physical meaning. Right? The physical operator, the spin, is completely invariant under that. So while that will have some physical manifestations, if we had real electrons for spins, we have to somehow fix the badness of this accidental symmetry that emerged when we wrote down this mean field Hamiltonian. And the way that manifests itself is that actually the kind of effective theory that describes this quantum spin liquid state is actually a gauge theory, where this Z2 symmetry gets elevated to the status of a gauge field. If you didn't understand that, it's okay. For the semiconductor, it's a similar thing. The semiconductor Hamiltonian, it also has a symmetry, it has a larger symmetry. It conserves particle number, so it has a U1 symmetry. So consequently, this actually becomes a spin liquid, which is what's called a U1 quantum spin liquid state. You might think it would also have a gap, since the semiconductor has a gap. And indeed, it does have a gap to spin excitations, but it actually, a U1 quantum spin liquid, we'll see, a lot of time, but okay, I'd like to explain. U1 quantum spin liquid is basically a U1 gauge theory. And you guys are actually familiar with U1 gauge theories. That's just a gauge theory of electromagnetism. And we know electromagnetism actually doesn't have a gap. It has a gapless mode, it has a photon. So these U1 quantum spin liquids that would be described by projecting a semiconductor are a little richer than these topological ones in some respects. Okay. Let's see what's left. Next one would be maybe the semi-metal. So a semi-metal Hamiltonian, like the Hamiltonian for a semiconductor, also conserves number. Okay, so this is also a different, also a U1 spin liquid, actually, except it already before projecting there's no gap for the fermions, and so the kind of spin liquid that results from that actually we believe is also has gapless spin excitation. So it's described by some theory of a U1 gauge field coupled to Dirac fermions. So this is kind of a quantum field theory problem. It's given the name of QED3. Yeah?
Sorry, when you're saying it's gapped according to what Hamiltonian, you act with the projector to the Hamiltonian of the wave
Yeah,
function.
I'm making statements that are, as I said, a little bit of religious belief. But, so far what I told you is this Hamiltonian is something entirely fictitious. We use it to generate a variational ground state. Okay. So what we believe, the way we generate a variational ground state is we take the fictitious ground state of this Hamiltonian and we project it back into the physical space. So this projection is basically fixing the number of electrons on every site. Okay. So you can think we're kind of fixing a quantum number, applying a constraint to every site in space independently. So there's the way in which we do such a thing in field theory, apply a local constraint, is to introduce a gauge field. That's what a gauge field does. It has a local symmetry generator at every point in space, and a symmetry generator is some object that commutes with the Hamiltonian, therefore expresses some constraint, and we choose it to be diagonal. Okay. So that's sort of the logic why this is connected to a gauge theory. A more practical question you could ask, how would I actually compute an excitation? You could imagine taking this mean field Hamiltonian and studying not only its ground state, but its low-lying excited states. They would be the ground state, say, of the superconductor plus some Bogoliubov quasiparticles excited above the gap. That's still not a good wave function, but I can project it as well. Okay. And that indeed is kind of, roughly speaking, the sense in which we think that such Hamiltonians describe the excitations of the system.
Can I ask a related question?
Yeah.
Is it obvious that the same Slater determinant could not describe a semiconductor and a metal?
Yeah, it's kind of obvious. So if I look at the Slater, if I can really only compare equal time quantities, I can compare expectation values in those states. And they're qualitatively different. So for example, in a metal, you have RKKY oscillations. There are long power law tails in the correlation functions of density or spin. In a semiconductor, those correlations decay exponentially because of the gap. There are qualitative differences in the long distance correlations of those states, even before projection. What's not obvious, okay, and which is not even true always, all right, is that if I take two free electron wave functions that are really in different phases, but I project them, that I don't end up with a new wave function which is very different from the original wave function. Could even be in the same phase. Actually, that will happen. If I try to do the second type of wave function here in 2 dimensions, the semiconductor wave function in 2 dimensions, I will find that the projection does something extremely drastic to it. And it will actually not be a spin liquid wave function anymore. But this will work in 3 dimensions. And that's related to something I don't really have that much time to talk about, which is stability of U1 gauge theories in 2 and 3 dimensions. So, more questions? There's a lot of material here. I can't cover all that well, I have to say. This is meant to be a bit of a guide, but I'm going to eventually turn to a very specific example where we can go through in some detail. Yeah, okay.
Are any of them
Yeah.
related to RDB wave function?
Oh yeah, so this one is basically the RVB. Why might you guess this is the RVB? You can work this out in quite a bit of detail, I mean, roughly speaking. So this superconducting wave function is very short range. It has a full gap for everything. It's all spin singlets. You can think about building it up. It's Cooper pairs. There's a way to write the wave function for the ground state of a BCS Hamiltonian, in terms of these coherence factors. And each coherence factor basically adds pairs to a state. So you can write the ground state with fixed number of particles of this BCS Hamiltonian as just a bunch of pairs in their pair wave function acting on the vacuum. And in a BCS superconductor with S-wave pairing, that pair wave function is very short range. It's because there's a gap. Okay? It decays within some coherence length of the superconductor.
But in explicit expression, the wave functions themselves are different.
Oh, yeah, sure. If I want to have, this in general will have, I guess this comes back to your question earlier, I will not just have nearest neighbor pairs. I can do that by fine-tuning these components.
So the statement is that the wave functions themselves are different in their explicit expressions, but the property of the states that they are describing are
Okay, this is a
supposed to be
great
the
question.
same.
Maybe it's good to talk about. Let me write one more thing and then we talk about that. Okay. The last example is a metal, which is, again, some U1 quantum spin liquid, but with a Fermi surface. So this is kind of a very popular problem to study. This is the problem of fermions coupled to U1 gauge field emerges in various situations, kind of an approximate approximated by the problem of a metal near a dramatic quantum critical point, and many other things are kind of similar to that. As we sort of go down this list, actually, we understand these field theories less and less. The top ones we understand, the first two we understand extremely well. Okay, so Una was asking about, well, what exactly do I mean by this wave function? Maybe that's a way to phrase it, okay? In general, you can ask, what do you mean by a wave function, okay? A variational wave function is, of course, it's useful in trying to get an approximation to the energy. But we know the wave function is not the exact ground state wave function. And you can ask, how close are you to the exact ground state wave function? Well, for an infinite system, you're always exactly wrong. So the overlap of any guess that you make with the exact ground state wave function is going to decay exponentially with the size of the system, the number of sites in the system. Because you make a tiny little error in one local region, that error multiplies as you take the system bigger and bigger.
But that's not really relevant, right? I mean, what you care about is per particle.
Well, you care about the energy per particle, but actually we care about some other features. So if we want to get the energy right, we're fine with this, okay, per particle. But we're interested in actually knowing is our wave function in the same phase. And that's sensitive to long distance properties of the wave function. So just because we get kind of local energies right doesn't mean that we're actually necessarily getting these long distance energies right. So, using these as kind of ways to find the best variational ground state has its issues. But what we hope is that we write a wave function which is sort of has all the right qualitative properties. The way to think about it is that quantum Hamiltonians, they generally, we can imagine varying parameters in our Hamiltonian. Hamiltonian is GH1 plus G2H2, where each of these are just local Hamiltonians, and there's some phase space, G1, G2 of parameters. And the ground states break themselves up into quantum phases. There'll be some region here, which is this quantum spin liquid one phase. There'll be some other region here, which is an ordered antiferromagnet. There might be some other region here, which is a valence bond solid. But generally, that's what we mean by a phase. A phase is something where, as I change parameters in the Hamiltonian, I remain in the same state. It remains qualitatively the same. The wave function, though, if I actually compare the wave function here and here, they're orthogonal to each other in the thermodynamic limit. Okay. But locally, they look kind of similar, and they should, more importantly, have the same long-range correlations. So what we say that there's some kind of adiabatic continuation that's possible to convert one Hamiltonian into another within this region. And so likewise, we would like to say, we hope that the wave functions we choose are adiabatically continuable to a generic wave function in that quantum spin liquid state. So is it actually true for those wave functions? It's true for the topological wave function, and it's not true for any of the others, I think.
How do you know that's true? True in what sense?
Okay.
Based on what?
So wave functions are great. Again, what is even better than a wave function is an effective low energy theory. Sorry, this is a question.
I don't want to interrupt that here. Yeah, okay. So I don't know if you're still answering.
Yeah, I was, but
Yeah, you
should I move to you next? Okay.
Yeah, you.
Okay. So a ground state wave function is great, but with it in hand, we can only compute properties in the ground state. We might want to know things like spin-spin dynamical correlation function. At least, by hand, we can't compute that from the ground state wave function. You can ask, could you deduce it from the ground state wave function, which is kind of a deep question. But certainly directly we can't compute it. So a more general object which would allow us to compute anything we want is a low energy effective field theory. That's what we really would like. We'd like to have an effective Hamiltonian or an effective action that describes the low energy physics. Okay. And so these are kind of effective field theories. we believe there's an effective field theory associated with each distinct quantum spin liquid phase, and we can derive it in some cases. So for the RBB slash Z2 quantum spin liquid, this effective field theory is a topological field theory, topological quantum field theory that can be written in many ways. It can be expressed as a double Chern-Simons theory. It has some expression in terms of the algebraic theory of anyons, etc. Lots of fancy things. Okay, but that's or a Z2 gauge theory. For this second one, the U1 quantum spin liquid, the one that corresponded to a semiconductor, this is really just electromagnetism.
But my question was, how do we know the very first one, which you are, sounds like most confident? How do I know the RBB wave function and your?
By many ways. I mean,
Yeah, so you measure different things?
There are many explicit constructions. You can actually find a limit where you smoothly deform that wave function to obtain exactly the RBB wave function. But you can also, many people have calculated properties in those wave functions and compare them to those that are predicted from these more field theoretic descriptions. For this U1 quantum spin liquid, the level is not as well studied, but again, we kind of know a limit of which we can find really derive the effective field theory directly from the Hamiltonian and compare it to properties of that wave function. In the other cases, I'm quite sure that in the other cases, the wave function is not exactly accurate for the effective field theory. We think the effective field theory is a more fundamental description than the wave function really. Today I wanted to talk about wave functions as kind of a guide to give you a little bit of intuition of how you might construct different spin liquid states and think about their differences.
It's a student's question.
Yeah.
I think you basically answered it. I think my kind of question was that, yeah, all of these statements are dependent on Hamiltonian. And your answer is basically that you know the effective field theory for each of these classes of spin liquids, so that kind of replaces knowing Hamiltonian for some lattice theory or something.
Well, so we know the lattice. We know lots of lattice Hamiltonians we're interested in. We know a lot of effective field theories, but we don't know how they correspond. So one very crude way to try to estimate how they correspond is to associate a variational wave function with each of the effective field theories and compare their energies for a lattice Hamiltonian. But it's very crude, not that reliable. We need to rely on people like Emmanuel and his friends doing numerics to make those comparisons better and better. Or we rely on experiment to test phenomenological predictions that come out of the effective field theory descriptions. Okay. So that's my plan for the second lecture tomorrow morning will be to do that. Okay.
Yeah, for the semiconductor U1 quantum spin liquid case, what prevents the generation of like a Chern-Simons term to gap out the photon?
That would be a different, that I wouldn't call that a semiconductor, that would be a quantum Hall state. So we could do something else, that's yet another spin liquid. I didn't list all of them. In fact, I'll give you a different example, that's yet another one. We'll talk about a state tomorrow, which is, instead of projecting an S-wave superconductor, project a P plus IP superconductor. Yeah.
These projected wave functions are no longer the ground state of your original quadratic free fermion
No.
theory, right? So is there a guarantee that they're the ground state of any?
No.
Is
No.
there a guarantee that they're close to the ground state of something that might resemble a...
Not really.
When you say they're variational, what are you computing the energy with respect? What's the
All
Hamiltonian?
these Hamiltonians have parameters in them, right? I can choose different hoppings in here.
Yeah.
But those are variational parameters if you want, okay?
But you don't know which Hamiltonian the projected wave functions actually correspond to as a ground state.
You don't. You try to make some educated guesses. So, you know, if you understand these free electron Hamiltonians, you know you could look at, for example, spin correlations in those free electron Hamiltonians, and you know they behave in certain ways. And now you can go back to your physical spin model and ask, okay, what sort of correlations, just at nearest neighbor level or something, would minimize that energy? Okay, I'd like something like that. I know that, you know, if I'm studying a triangular lattice, I want my spins to be roughly 120 degrees from one another, so the nearest neighbor spins have to be anti-correlated. Trying to do that. But it's a heavily numerical procedure, and actually you have to compare all these things. So there's a big technical apparatus that I didn't talk about, which allows one to systematically construct these quadratic fermion Hamiltonians. That's something called projective symmetry group analysis. Basically, you specify some symmetries you want the system to preserve, and we can delineate all possible these free fermion Hamiltonians. And then it's some big job of variational Monte Carlo, somebody to actually compare energies of them. Okay. This is one approach. I only really presented this approach because it allows you very simply to list several different types of spin liquids, all in terms of the same construction. Okay, is it the best approach? But by no means is that obvious. So the example I want to talk about tomorrow is really, you know, theoretically based on Kitaev's honeycomb model, which is an exactly solvable model. I don't need any of this apparatus, and we just solve the Hamiltonian. Kitaev could, and we can copy him. Okay. But you know, that's a rare thing, whereas this construction can be applied. It's a good numerical tool that lots of people use. There are other types of models that are more soluble or other techniques. Lots of guesses and intuition applied. All of these problems are problems with basically no small parameter. You need intuition, input from experiment, things like this. Actually, it's been a problem, okay? Because there's so many quantum spin liquid phases, it's not obvious, you know, which is the right one, and you have so many choices to try to compare them to limited experimental data on the experimental candidates. So it's particularly interesting to focus on states for which there is some sharp signature. So that's going to be the point of the second lecture, is to talk about sharp signatures, which are not general. Not all quantum spin liquid states have those sharp signatures, but some of them have some sharp signatures that we can look for. And there's a recent rather exciting experiment which I want to talk about. Might have shown one of those.
All right. That ends today's lecture. Let's thank Leon again.